Good morning, Honors Math 3. Let's see, we're going to finish up task 7.3 today, which is our geometric sequences. If you printed off the notes for today, that's great. If not, you can work through these on some loose leaf. These first two examples are just a little review. If you were asked to find the sum of that sequence, stop and think for a second how you would find the sum of the first 11 terms of that sequence. Look at it for a second, and then think about how you would find that sum. Okay, if you look carefully at that before you plug into any formulas that you know, this is an arithmetic sequence. The way we can start to tell that's an arithmetic sequence is because this is linear. 2k plus 3 is a linear expression. So it is an arithmetic sequence with a common difference of that slope, which is 2. Since it's an arithmetic sequence, I can use the formula for the sum of an arithmetic sequence, which is n over 2 times the first plus the last, in this case from 1 to 11. Number of terms is 11. 11 divided by 2 times what is a sub 1? A sub 1 is plug in 1. 2 times 1 plus 3, which is 5. Plus the last, in this case, is a sub 11. What is a sub 11? 2 times 11 plus 3, which is 25. And I get a sum of 165. You could have used other formulas for that, but if you notice it's arithmetic, it's a little bit easier. This is a geometric sequence. A sub 3 is 2 ninths. A sub 6 is 2 over 243. Quick review from yesterday, find a sub 12. How do you find the nth term of a geometric sequence? It's always the first term times r to the n minus 1. Think about what you need to find and start to find those things to find the 12th term of this geometric sequence. Pause and try that. Okay, let's see if we agree. Between the third and the sixth term, there's 3 common ratios. So I go from the a sub 6 will be the third term times r to the third. I solved for the common ratio. You can stop and check, and I got a common ratio of 1/3. So let me start to plug that into my formula. 1/3 for the 12th term, I'll have 11 of those common ratios. Now I need to find a sub 1. Between the third term and the first term, there's 2 common ratios. So I plug in the third term is equal to a sub 1 times that ratio squared is 1/9. Multiply both sides by 9. And I get that a sub 1 is equal to 2. Let me plug that in. And that gives me the 12th term of this geometric sequence will equal, my numerator will be 2 times 1 to the 11th. My denominator will be 3 to the 11th. And I pick up my calculator and get 2 over 177,147. Easiest to keep that as a fraction. Alrighty, we have 2 more formulas to add to our list, and then that will be complete for our formulas for this little module. We can find the sum of the terms of a geometric sequence. The sum of the first n terms of a geometric sequence is s sub n is equal to the first term, a sub 1 times, there's a ratio in there, 1 minus r to the n over 1 minus r. Obviously, that is a more complicated formula than what we're used to. The sum is the first term times the ratio of 1 minus r to the n over 1 minus r. Here's a geometric sequence. I know it's geometric because this looks exponential. It has a common ratio of 3/5. And we start to recognize that formula, that first term, a sub 1 is equal to 2. Find the sum of the first 15 terms of that sequence. The sum of the first 15 terms will be the first term, 2, times 1 minus, my ratio is 3/5, raised to the nth power, 15 terms, all over 1 minus 3/5. Okay, that looks ridiculous, so I'm going to plug that into my calculator. Pick up your calculator. 2 times, you will need parentheses for the numerator, divided by, I would just put that in parentheses also. Plug that into your calculator and I get, pause and plug that in, I get 4.998, or about 5, the sum of those first 15 terms. Pause if you would, and just in general, jot down a formula to find the sum of the first n terms of this geometric sequence. Notice what a sub 1 is, and try to figure out what your common ratio is, and then find the sum of the first n terms. Okay, I notice the first term is 2/5, and every time I'm multiplying by 2, so my common ratio is 2. Plugging into that formula for the sum of a geometric sequence, 2/5, the first term, times 1 minus 2 to the n over 1 minus 2. Let me clean this up a little bit. This is simply negative 1. Negative 1 times 2/5 is negative 2/5 times 1 minus 2 to the n. And that's the most I can do for any number of terms n. Alrighty, now we continue on a little bit to find the sum of an infinite geometric series, we call that. An infinite sum means I start with a term, add it to that term times a common ratio plus that term times that common ratio again. So I'm adding up a geometric sequence, but forever. I just keep adding and adding and adding and adding. So there's no ending spot. There's no end. I just keep adding and adding and adding. So we write this as the sum of this infinite geometric series, we call this, is the sum from k equals 1 to infinity of a geometric sequence, a sub 1 times r to the k minus 1 for an infinite sum. Okay, before we find the formula for the sum of an infinite geometric series, consider a case, let's say the first term a sub 1 is 5 for this infinite sum. And let's say our common ratio is 2. That implies that this infinite sum would start with 5, and then I'm going to add it to plus 5 times that ratio, plus next term, I'm going to add in another of those common ratios, plus add in or multiply by another of those common ratios, and keep adding this up forever. Think about what that sum would be if I added all of those terms. Now consider, again starting with 5, but with a common ratio of 1/2. That implies my first term would be 5. I'm going to add it to my second term, which is going to be 5 times 1/2. Add that to my third term, which is 5 times 1/2 squared, plus 5 times 1/2 cubed, and keep adding and adding and adding. What would this sum eventually be? Versus what would this sum eventually be? If you notice, these terms just keep growing and growing and growing and growing and growing. So this sum is going to keep growing. But somewhere along the line, 5 times 1/2 to the nth power, which is huge, think of n approaching infinity forever, growing. This, a fraction to a huge exponent, actually becomes 0 as n gets larger and larger and larger. So these terms are all shrinking and shrinking and shrinking and shrinking and approaching 0. Okay, let's think about this sum more analytically and prove a formula to find the sum of an infinite geometric series. I'm going to distribute this a sub 1, and this becomes a sub 1 minus a sub 1 r to the n all over 1 minus r. I'm going to separate this into two fractions. So it's going to be a difference of a sub 1 over 1 minus r minus a sub 1 r to the n over 1 minus r. Now think about these terms as n gets huge. Like we saw up above, for this ratio, if that ratio is a number that's raised to a power and keeps growing and growing and growing, when that ratio is bigger than 1. But when that ratio is a fraction less than 1 and I raise it to a huge power, this thing approaches 0 only if that ratio in absolute value is less than 1. Well, if this approaches 0, this whole fraction approaches 0, and if that ratio is less than 1, then an infinite geometric series has a sum And that sum, if this approaches 0, I'm left with this. The sum of that infinite geometric series from k equals 1 to infinity, r to the k minus 1 will equal the first term over 1 minus r. Okay, we take a little aside here. It's almost a calculus concept. If there is a finite sum as a number approaches a number L, as n approaches infinity, then we say that that infinite geometric series will actually equal a number L. And we say that that series is convergent. If it actually converges on a number, on a sum, that number is L, and we say the series converges. And if the sum does not converge to a number L, it just keeps growing and growing and growing, or shrinking and shrinking and shrinking. If the sum does not converge to a number, we call it L, then we say the series is divergent. And this happens when the ratio is greater than 1. Okay, here's an infinite ... geometric sequence. We call it a series. Let's see. If it converges, find the sum. If it is not convergent, then we call it divergent. Really, all we need to do is we need to check for that ratio. We need to check for the common ratio. Always take a term divided by its previous, term divided by its previous, 16 divided by 12, which reduces to 4/3. Oopsies, 4/3 is greater than 1. That implies that there is no sum, and the series is divergent. Okay, well, certainly let's find a case where we have an infinite geometric series that does have a sum. Here's an infinite geometric sequence. The ratio is 1/3. 1/3 is less than 1, so that means that there is a sum. Let's find it. The sum of that infinite geometric series will always be, let's use that formula. It's an easy formula. First term divided by a sub 1 divided by 1 minus r. A sub 1 divided by 1 minus r. What is a sub 1? Plug in 1, that goes away. 1 minus 1 is 0. Anything to the 0 is 1. So again, that is my first term, a sub 1. And a sub 1 will be 8 divided by 1 minus the ratio. The ratio was 1/3. I get 8 divided by 1 minus 1/3 is 2/3. 8 times 3/2, which is 12. Really amazing that we can add an infinite number of terms and keep adding and adding and adding and adding all the terms of that sequence for the rest of our life. And the sum becomes 12 because those terms become closer and closer and closer to 0. All right, just food for thought. Here's a question for you. Draw a little picture and think about how you would answer this question. I'm going to pause so you can work through something. And we'll start to form a formula list very soon. Okay, if you set up a picture here, we have 30 tiles in the first row, or 30 feet wide, I should say, in the first row, 15 feet wide in that last row, but they are 12-inch by 12-inch tiles. So there are 30 of them here and 15 of them here. If you notice, since I'm subtracting 1 tile from each row, this is actually an arithmetic sequence. So we have to work in the next couple of days to recognize what's what. This is an arithmetic sequence. Do we need a sub n or the sum s sub n? How many tiles will be required? Is actually s sub n. And the sum of an arithmetic sequence is n over 2 times the first plus the last. And we want to find the sum. Pause and think about what you need to find. Okay, if you notice, plug into the formula, I know the first term was 30, the last term was 15. I really just need to find n, the number of terms. Last term is 15, first term is 30, plus n minus 1 of those common differences, which is -1. I solve this equation for n, and I get n equals 16. So I want to find the sum of the first 16 terms, 16 rows, which is 8 times 45, and I get 360 tiles are needed. We're going to wrap up through 7-3 with some kind of quest